Here we have a current balance. A current balance can be used to measure the force between two current-carrying conductors, and it can also be used as an ammeter. It was one of the first ammeters. Here's a schematic of the current balance. We can have a current flowing through the lower wire H, and we'll call that current I. And we can have a current flowing through the upper wire T. We'll call that current I sub 1. If I sub 1 and I are flowing in opposite directions, we'll see that the two wires T and H will repel. Conductor T can move because it's just balanced on these two posts. You could add weight to this little platform on wire T and bring the two wires back to their original separation. The weight you've had to put on T to get back to the original separation is the amount of force that wire T is experiencing. This wire along the z-axis represents this conductor H of our current balance. This segment represents a differential current element in our conductor T of our current balance. We've applied the Biot-Savart law to an infinite line of current. If we treat this lower conductor of our current balance as if it were an infinite line of current, we know that its magnetic field intensity would be given by this expression, I over 2 pi rho in the phi direction. We found that by applying the Biot-Savart law, and it also agrees qualitatively with the experimental results using the iron filings around an infinite line of current. We're going to find the force on this upper wire, but it will also be confirmation that the Biot-Savart law gave us the correct magnetic field intensity. The force on a current element I sub 1 dl is mu sub 0 I sub 1 dl cross into the magnetic field intensity. For I sub 1 dl, I'm going to substitute I sub 1 dz in the minus z direction, and for H, I'm going to substitute I over 2 pi r, where r is the separation between our two wires, in the phi direction. Along our upper conductor, the phi direction is out of the page and the z direction is to the right. So AZ cross A phi is in the minus rho direction. We have our magnitude for the force on our differential length of our upper wire, and it's in the plus rho direction, so these two wires are going to repel. To get the total force on the upper wire, we will integrate from 0 to L, where L is the total length of our upper wire of our differential force. Here is that total force. There will be some error because we approximated our magnetic field intensity as if the lower conductor was of infinite length. To use this as an ammeter to measure some unknown current I sub 1, what you would do is put a known current I through the lower conductor, and then from the amount of weight you have to put on the upper conductor to return it to a separation of R, you obtain the force. And then you can solve for I sub 1 because you know all the other entities in this equation.